So Franco, what a privilege it is to have you joining us today. Franco has considerable experience in tectonics, ore deposit geology, and mineral exploration from many parts of the world. And it's going to be incredible hearing from him today whilst he talks about alkaline complexes, carbonatites, rare earths, and their significance in modern technology. So thank you so much, Franco, for your time today. Awesome.
So this talk will be about carbonatites, alkaline complexes, and the association of these systems with rare earth mineral systems. And what do they mean in modern technology? Right, in this presentation, we go through, first of all, introduction and overview. Then we look at key examples and the role of mantle and subcontinental lithospheric mantle. Now, first of all, you must understand that the main consumers of rare earths, China, obviously, USA, Japan, Korea, and Thailand, with China reportedly accounting for about 60% of the world consumption. Now, this was done in about 2 years ago. It's probably more or less, but it gives you an idea of the role of China in the rare earths metals. Now, this shows the percentage of global rare earth oxides split by country on the left and deposit type on the right. So as you can see, China has 43%, followed by Russia. Australia doesn't do too bad with 10%, and so on. In terms of mineral deposit type, most of these deposits are in carbonatites. IOCG, iron oxide, copper, gold, and alkaline complexes, laterite, and tailings. The carbonatite takes more than half of the total of the rare earth oxide resources. Now, the other thing, what do we do? Current use of rare earths? Well, as you can see, catalysts, magnets, batteries, metallurgy, polishing, ceramics, glass, and so on. So it's obviously an extremely important situation for these metals. Now, rare earth elements, also known as lanthanides, comprise metallic elements with atomic numbers ranging from 57. Some of you may know this already, but just in case for the general public, atomic numbers ranging from 57 to 71. And we have lanthanum, cerium, praseodymium, neodymium, samarium, and so on, and so on, and so on. Now, important to realize that yttrium is also included in the rare earths because it shares similar chemical properties and generally occur in the same deposit. Now, the most common minerals rich in rare earths are bastenacite, monazite, xenotime, and allanite. So these are the ones that are most commonly found in the periodic table. The rare earths, lanthanides, actinides occur at the bottom here, as you can see here. And also, we have light rare earths element and heavy rare earths element. The light rare earths center, lanthanum to europium, and heavy rare earths center, gadolinium down to yttrium. As I mentioned earlier, yttrium is considered rare earths because it's not a rare earth, but it does share chemical similarities, and therefore it goes into heavy rare earths. What is in a name, just for a general purpose? Lanthanum, from the Greek lanthanum, which means I'm hidden. Cerium, from the Roman deity of fertility, Ceres. Praseodymium, from Greek praso, meaning leek green, and dadamus, meaning twins. Neodymium, from the Greek neo, which means new, and didamus, which means twin again. Promethium, from the Tata Prometheus, who brought fire to the mortals. These are all very old names that go into the Western legend. Samarium, europium, from the continent of Europe. Gadolinium, from Johann Gadolin, 1760-1852, to honor his investigation of earths. Terbium, I'm not going to go through all this, but essentially, as you can see, and of course, the terbium from village Terbi in Sweden. Lutetium, from Lutetia, which is the city, which the Latin name for the city of Paris. Now, the Australian government list of critical minerals published in 2020. There's a HTTPS that you can access yourself if you wish. But in the next slide, it shows everything. And it shows that the China, antimony, beryllium, all the critical metals are listed there. Niobium, platinum, and so on and so on. And as you can see, China does occupy a huge amount of all this. Antimony 63%, bismuth 74%, gallium 97%, germanium, and so on and so on and so on. Just to give you an idea of the distribution of the economic resources on the largest producers in 2019. Now, rare earth minerals, basenasite is probably the most important rare earth minerals, monazite, xenotime, apatite, and these are the ones that actually carry most of the rare earth minerals. Now, what do we do with these rare earth minerals? Well, basically, there it is. You have energy efficiency, compact fluorescent lights, hybrid vehicles, weight reduction in car, wind turbines, autocatalytic converter, diesel activity, and of course, flat panel display, disk drive, digital cameras. As you can see, obviously, it is extremely, extremely important. Rare earth metals, also military application, unfortunately, but that's how it is, and anti-missile defense, smart bombs, satellite system, jet fighter engine, and so on and so on and so on. But that's, I'd rather stay away from this. Now, in terms of rare earth deposits, where do they occur? We have magmatic and sedimentary. In a magmatic deposits, carbonatite, peralkaline, and pegmatite rocks are the ones that carry most of the rare earths. Any sedimentary system, you have residual placid deposits, phosphorites, ion adsorption clays. But I will focus on the magmatite, particularly the carbonatite. So rare earth mineral system, general characteristic occurring carbonatites, as I mentioned earlier, with bastenasite, monazite, and ferrocarbonatite, and hydrothermal mineralization of the same. And of course, in alkaline silicate rocks, we have silica saturated, silicon saturated, and naturally hydrothermal deposited derived from the above. And here the veins, breccia, penites, bastenasite, monazite. I should point out, in case some of you are not aware of it, phenite is the alteration halo which surrounds carbonatite. We'll go back to that. Rare earth minerals and Austin lithologies, we have bastenasite, and the CRB is a carbonatite, HMD, hydrothermal metasomatic. And I should point out, hydrothermal metasomatic can be directly derived from the carbonatite. So we have bastenasite, parisite, sinchisite, various types of fluorocarbonate, and monazite I mentioned earlier, xenotime, churchite, fergusonite, and loparite. These are the minerals that we're talking about. Now, rare earth mineralization is generally associated with potassic rock, carbonatites, and nephilitic rocks. In other words, with rocks which occur in a specific tectonic setting. They are highly fractionated, metaluminous, and peralkaline granite intrusion can be enriched in rare earth element, which is increased by further chlorine and fluorine-rich hydrothermal fluids activity. Surfacious clays and laterite may also have high concentration rare earth elements, but I will not be talking about that. This is a simplified map showing the distribution of carbonatites across the world. And as you can see, there are quite an awful lot of them. Please ignore that this is taken from a recent special issue in our geology reviews, and those shown in red are the ones discussed in the special issue. But it does give an idea, nevertheless, of the huge amount of the carbonatites across the world. But more important, I want to draw your attention to the East African rift system, which is particularly well endowed with the carbonatites. Distribution of earth deposits where a carbonatite associated, alkaline igneous rock associated. And I should point out that carbonatite alkaline igneous rocks quite often occur, have a very close association. Although you can have just carbonatite and no alkaline igneous rock, or you can have alkaline igneous rocks with carbonatites. Now, carbonatite are intrusive, igneous, abyssal, igneous rock in which the carbonate minerals are primary. Apatite and pyrochlore are often considered essential, and other accessory minerals, siderite, calcite, dolomite, ankerite. a less common accessory mineral, magnesium-rich magnetite, phlogopite, and pyrite. Let's look at some key examples. This is the one I'm very proud of because I discovered that a long time ago in 1996. And it's a Copperhead carbonatite in East Kimberley. I was with my friend Craig Ragles when I discovered that, quite by accident, I should say. And the accident was a Copperhead is actually a snake. And as a snake came towards me, I ran away and found this carbonatite plug. Carbonatites are generally plug-like intrusion and occur as small subvolcanic intrusion, as veins and dikes associated with alkaline ring complexes. And naturally, needless to say, carbonatites are a major repository of rare earth minerals. The one I talked before, the Copperhead carbonatite, did some work later on that. There it is. You can see it here. And this is the kind of a geological map, if you wish. We published that in 1996. And no one has ever been since. It's incredible. It's a carbonatite system. No one in the Kimberley, no one ever looked at it again. But there it is. That's the geological map. It's a carbonatite albitite complex. There's a lot of albitite in it. But basically that's what it is in a very remote area of Kimberley. That's what it looks like under the microscope. Lots of calcite, obviously, sodic amphibole, and the breccia pipe you can see here. Now, this is important because as I mentioned earlier, this is what the carbonatite, a full system of carbonatitic material comes here. The servite is a calcium carbonatite, okay, so it's called servite. And then, of course, you have a halo of alteration around it, which is called phenite. These may occur in volcanic systems, and in fact, one volcano which has the carbonatite, the carbonatite volcano is Old Daniel and Guy, which I'll show you in a minute. But also want to show you the level of erosion that normally we look at. At the bottom, you can have this level of erosion, and you look at the servite, phenitic alteration, or that level of erosion, or that level of erosion, or that level of erosion. Obviously, if you are up here, then there is a huge potential of finding carbonatites below that. Excuse me. This is Old Daniel and Guy. And in 1966, nobody realized it was actually a carbonatite volcano. And that's because when the lava comes out, it's black, and they thought it was basaltic. And then as it evolved, in fact, it's all it is just carbonatite and nothing else. Anyway, 1966, eventually, the message came through that that is a live carbonatite volcano. Now we have various types of carbonatites, calcium carbonatite up at the top here. You have magnesium carbonatite and ferrocarbonatite. I was involved with the discovery of a major ferrocarbonatite complex in Western Australia. I'll come back to that later. Here we see a hypothetical carbonatite mineral system. Okay, I won't go into the great details, but essentially when you have disseminated pyrochlore, you have that's the carbonatite through here, phenitic alteration on the other side. Now, very important to understand, don't worry about all these subdivisions up here, but basically the carbonate and the silicate, at one stage, they are immiscible, they occur separate. And then as the pressure and the temperature decreases, they can mix or they can separate. But the carbon and silicate, I'll show you some very nice slides in a minute. So carbon miscibility, and eventually they separate, and you have carbonatites on one side, carbonate lavas, carbonated breccia tuffs, and nephelinite, and so on. Always associated with alkaline. So this is the evolutionary trends on nephelinite and carbonate magmas. Here, they're together, and then they split. Now, let's look at Western Australian carbonatites. A Copperhead I've talked to you before was up here. Then we have the Gifford Creek. I was heavily involved in the mapping of this one here, and Mount Weld the Ilgan Craton. I've visited a few times, and that's an interesting one because I'll show you why in a minute. So let's first look at the Giffocrid ferrocarbonatite. Oops. Okay, there it is. So what you have here is a series of sills, and they look like dolerites, and that's what I thought it was, dolerite. It's not. They're actually ferrocarbonatite. That's interesting. So you have a series of ferrocarbonate sills, and then from here you have various. This is a zone of carbonatite alteration, phenitic rocks, and more carbonatites coming in this way. So there are two stages: one which along the lines of River Fall, another carbonate which came much later. Now, this is interesting. This is a thin section. So you only look at 5.5 centimeters, but it's very, very, and by the way, an example, immiscible carbonate liquid in a silicon melt, but very, very active. Look at this. You got one here, you got one after the other, one after the other, one after the other, in a 5.5 centimeters long section. It's extremely active. And you have carbonate globules, you can see here, in a quench texture silicate, which is sodic amphiphil. And that's what they look like. Okay, so you got a photograph, and here you have your iron carbonate globule here. Okay, and here you have the iron oxide that replaces the iron carbonate because of weathering, and this is the silicate in between. So this is a beautiful case of immiscibility texture between two liquids, iron carbonate and alkaline silicate. Now, the other interesting thing is that, as I mentioned earlier, you have phenitic rocks which are result from the alteration related to carbonatites. And when you look at these rocks, at least the first time I looked at it, I thought it was like some kind of a cyanide. It isn't. It's such an orthoclasite, and further investigation shows that in fact it is a proximal stage of carbonatite phenitic alteration. And here you have instead distal stage that there's your carbonatite here and phenitic alteration on both sides. So let me go back a minute. So what you see here is a complete, very proximal, very close to the carbonatite phenitic alteration here and further away, distal. Now, there are various minerals which can be detected: ankerite, dolomite, calcite, obviously, arfentonite, ripekite, parachlor, carbonite, and so on and so on. This was XRD and the scanning electron microscopy, conventional microscopy, which shows all these minerals that are present. Yeah, right. And here we have the parachlor crystals that they are, monazite crystals, and of course nepheline, which is colorless, and ripekite blue. But also interesting, you see flow textures. Okay, and flow texture does indicate that there's obviously a very dynamic system which flows. Giffocrid carbonate sits up here. And my point here, which was opposed by others, is carbonatites are part and parcel of large igneous provinces. Okay, and that's where they occur, particularly in East African rift system. But here you have the Warakurna lip, which covers all this area. And sure enough, the Giffocrid carbonate, which is the same age, occurs right there. And obviously, I think there might be other places as well. But, you know, Western Australia has a lot of exposures are very, very poor and not easy to detect these things. But I would suggest that there must be other carbonatites somewhere along here. Now, when we look at the Giffocrid carbonatite, you have the first, we have two ages, 1075 and 1050. This is very important. So 1075, the carbonatites, ferrocarbonate silts and dike up here. There's a halo of phenitic alteration at the top, as you would expect. And as the thing evolves, okay, then you form the phenitic alteration from a larger halo, but also you have iron oxide veins which emanate from the ferrocarbonatite silts. We published two papers in the Australian, one in LITOS, one in OSIMM, Australian Oil Deposits, giving ages of the Giffocrid carbonatite. We have an age of 1075, an age of 1050 million years. Then later on, Z et al. Produce other ages, which go 1,360 to 80, 1175, and 1075. So they concluded that the emplacement age is 1361. Okay, maybe so, but I don't agree with that, because the age conundrum does persist, as I will show you in a minute. And this is the latest one from Spandler, and you see more ages. These the age of the Gifford carbonate, 30-70 million years. I doubt that very much. I mean, I'm not disputing the actual age, but I'm disputing the emplacement of the ferrocarbonate has got nothing to do with it. Now, let's go to Mount Weld, which, as everybody knows, it's a very beautiful place, by the way. And also, you really can't miss it, because look at the aeromagnetic magnetic image. You can't miss this thing, this bubble here as Mount Weld. And that's what it looks like in cross-section. That's the Mount Weld carbonatite. And you have various deposits sitting above, which are related to a supergene zone. And that's the supergene zone. You can see it here, Mount Weld lateritic ore. But the Mount Weld lateritic ore sits on top of a natural carbonatite. So the Mount Weld servite, which is a calcic carbonatite, contains apatite, mica, magnetite, apatite, phlogopite. I'm not going to go through all that, but a lot of it. And the regular resource published in 2011, I think. And you find that 250 million tons, 18% P2O5, 270 million tons, 0.9% niobium oxide, 145 million tons, tantalum oxides, and so on. This is 2011, so it actually may be more by now. But they give us an idea, nevertheless. It's just there to show you, give an idea of the content of the mineralization in there. Now, this is interesting. When I looked at the Mount Weld, you see this breccia here, there's a core, and here you have an apatite cumulate. And when I looked at that, you actually see shard-like textures of agglutinated carbonate ash. So, in other words, we're looking at a volcano. We're not looking at an intrusion. The Mount Weld is a volcanic system, and you can't miss that, because when any volcanologist will tell you that these are agglutinated carbonate shard-like textures, these are carbonatite volcanic systems. So, in thick section of pyroclastic texture, compaction, partial welding, many carbonatite Mars is a volcanic breccia. In Tanzania were formed by processes of phreatomagmatic activity, and pyroclastic deposits agglutinated carbonate, which is what we've seen before, which is this stuff here. Agglutinated carbonate ash near the vent, polycrystalline dolomite calcite, teardrop lapilli supported by secondary sparry calcite, shard-like textures agglutinated carbonatic ash, spherical fragments, and so on, which again, like I said, this is what you see here. And back to Mount Weld, I published this work in Gondwana Research and also in the OSIMM Australian ore deposits. And you can see this, what up here you see lateritic material, laterite cap, but in fact, below that, you see like this carbonatite breccia vent fasces, agglutinating ash, carbonate servite before, and that's what it looks like. It's just shard-like textures, agglutinated carbonatite ash, which indicates a volcanic system. Now, the East African rift system is the motherland of the carbonatite. Make no mistake about it. You can see it here. Look at this. All these little dots, they are carbonatites. To the East African rift, it's just amazing. From the Red Sea through the Ethiopian rift, Lake Tanganyika, Lake Malawi, and so on. Palabora is much older, and of course you get all these carbonate systems along the west coast of Southwest Africa, and I'll show you why. There it is. When you look at, so let me go back a minute. So we're now looking at this area here. And there it is. You have alkaline complexes, carbonatite complexes and kimberlite. Oh, and by the way, many carbonatites are associated with alkaline complexes. So they come missing me. You got these major transform directions along which you have all this amazing amount, and all the same age, by the way. Damaran alkaline province, Luderitz alkaline province, Kubus-Bremen alkaline province, and so on. And let's go a bit further than that. So there it is. And that's because these, let me go back again, these major structures, transform direction, result from when South Africa separated from South America. And all along here, you have these major carbonatites, kimberlites, and other systems. And anaerogenic ring-time complexes shown in black, there are quite a few. Okay, this is the Irongo, this is the, I think the Bramberg is one of these here. It's quite amazing. There you go, the Bramberg, that's right. So the Bramberg is one of them. I think the Bramberg, if I remember correctly, I think it's probably this one here. Okay, these are granitic intrusion. That's the Etendeka plateau, which is a large igneous province, Etendeka plateau, which is a basaltic rocks. Same age. And then you have the Bramberg complex, which actually punches through the lavas. There's a flood basalts, which is the Etendeka, and the Bramberg punches through it. And by the way, it is also the tallest mountain in the area. It's about 2,000 meters above the desert floor. And like I said, there's Paranite-Etendeka lip, large igneous province, that's what lip means, 130 million years. And many of these carbonatites occur with the large igneous provinces. There's an example still in Namibia, Okorusu complex. There it is. I won't go into great details, but it's a partially carbonated nephelinite and indeed also carbonatite. The Okorusu syenite-carbonatite complex contains iron ore, platiniferous magnetite, fluorspar apatite, and the fluorspar apatite occurs as disseminations in orthoclasite, as veins, deposits along fractures, and as replacement in limestone units. On the Rokuma, there's a carbonatite complex. Just to give you an idea what these things look like. This was given to me by Kinloch Resources. I don't have many details. Kalkfeld is another one. These are the same sections, and this is the Quaggaspan carbonatite complex, as you see here, and the carbonatites right at the top. Now, there are many others in the Bushford, in the area of the Bushford complex. Palabora is one of the largest, and they have Goudini and Crifontaine. These are the ones I was lucky enough to visit and to study myself. Palabora, I won't go into great details, but the Palabora are quite a famous copper deposits. And there's the carbonatites up here. And it contains chalcopyrite, bornite, magnetite, apatite, phosphorites, badellite. The Goudini, I've shown you before, so let's go back a minute. Okay, Goudini, it's one of these here. Goudini and the other one here. Okay. It's a simplified Goudini carbonatite complex, and these are the carbonatite layers. It's like a ring structure, a ring complex. And this is the immiscibility. When we look, and this is incredible because this is a thin section scale. That's why I put that here. And you have immiscibility within the carbonate and a silicate liquid. So that's the carbonate, and that's the silicate liquid. They immiscible. And then as the temperature decreases, the pressure decreases, then they get back together. But at one point, they are separated. And here is a beautiful example of separation. Crifontaine, carbonatite. It was a pleasure to study that when I was in South Africa. I'm not going to go into details, but there it is. And Crifontaine again, you see the carbonatite tooth. When you look at these rocks, it's not easy to realize they are actually carbonates, okay? But as you can see here, who would call that a carbonate? Well, it is. It's just carbonate, nothing else. Bayonobo. Oh, this is quite incredible because Bayonobo is the largest rare earth deposit in the world, and it was initially mined for fluorite and magnetite until they eventually found out that, in fact, is the largest rare earth producer in the world. And there it is. These things look like banded like that, bastnasite, flanked by fluorite and granite edgerine, and banded fluorite, edgerine, and bastnasite. And two pits, main pit, east pit, just to give you an idea of what this thing looks like. And under the microscope, there's bastnasite through here, and the cancrinite. Now, as I mentioned earlier, the problem, the age, multiple age controversy, the age conundrum is a bit of a problem because depending on what you actually date, and Bayonobo is a good example. Ages range from 500 million years to about 1,500, 1,200 million years to 2,000 million years, depending on what is that you actually date. So you have rubidium, strontium age, samarium, neodymium, and zircon age is a range of ages. And that takes us back to the Gifford Creek carbonatite, which seem to have different ages. But the two main ages are related to a large igneous province at 1075 and 1050 million years. Bayonobo, we recently published a paper in Geology with my Chinese colleagues. And here you have the lithospheric mantle, mafic ultracarbonated magma immiscibility, and it goes up. Eventually they separate, producing a carbonate silt with rare earth rich ore, and this is what we see now. But it goes through all these processes. Okay, so the mafic alkaline carbonated magma immiscible, and then they start separating. You have alkaline magmas, and eventually calcium carbonate magma gets separated. And I'm not going into details here, but essentially here is the differentiation pattern of carbonatite from ferro to magnesium. Ferrocarbonate is what we mapped in Gifford Creek. In Gifford Creek, and then you have magnesium carbonatite, hematite, magnesium carbonate, rich magma, and phenetic alteration, which surrounds the intrusion, as well known. I was in Mongolia about 2 years ago, and here has a beautiful, look at that, you can't miss that. You see this white rock? Well, that's carbonatite, that's what it is. And back to the miscibility, also there, this is from here, by the way, from the Mongolian one, you see this immiscible material, and again you have calcite, dolomite, ocelli, which do represent the liquid immiscibility. That's what they are, it's just amazing. And carbonate petrography, there it is, and again, does suggest a volcanic system. Tom Tor is a famous one. I'm not going to great details. I don't know much about this. This is from my friend Raymond Seltman and Alexander Yakubchuk. But basically, it's part of this very large deposit of rare earths. Tom Tor carbonatite plug, there it is. Okay, there's a big one through there. Back in it was quite a bit of a shock because this is my home country, and here we have. We never realized for many years that the Mount Vesuvius, the Phlegraean fields, and this volcano here possibly relate to some kind of a quaternary faults or maybe subduction, but nothing to do at all. These are all related to east-west trending fractures. Again, alkaline fractures which produce alkaline volcanoes. Alkaline in Vesuvius and alkaline volcanoes, as in the Phlegraean field, as this one here, Vulture. And there are others, of course, in Italy, but I'm not going to great details about the Roman volcanic province. Have lots of carbonatites. But this is what he put together with my friend Franco Stoppa. He put a slide that shows the production of. Let me go back a minute so we understand. So we're now looking at this system here. Okay, so you have a volcano which is still there, by the way. It's quite a tall one too, but incidentally, and you have a extrusive carbonatite coming through here. Servite, which is a calcic carbonatite. various type of alkaline cyanitic system and so on. So this is a carbonatite volcano. And there it is. All right. So you have something like 80 tephra layers cut, but that's a fluvial channel. 80, so they're very, very active, very dynamic system of pumice, ashfall, and so on and so on. 80. I mean, I'm not going to count them, but believe me, these are 80 tephra layers. Amazing. And when you look at it in details, they are carbonatite lapilli. This is quite an incredible thing because it shows active venting of carbon dioxide near this volcano we're talking about. It emits like 500 to 750 tons a day of CO2 H2S. And also because of that, it's an ancient sacred site dating back to 3,000 years before present. And there it is. And this thing goes blah, 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 goes about it. It's just amazing to see how this works. This is an optic scheme of carbonatite, fluorocalcium carbonate, and fluoride deposit, and various relationship. So you have a, hang on, let me put this thing away. Oops. Right. Oop. Ah. Okay. Okay, so you have a series of events, high temperature, carbonatitic tuff-site, porphyritic carbonate, and as you move this way, you go to microporphyritic veins and aureoles in up here. Role of the mantle, subcontinental lithospheric mantle, that's important. So mantle dynamics and carbonatites. They form along rift. We see in East African rift, this is a good example. Form around cratonic margin, usually following weak zones of regional belt. Crustal scale, ductile to brittle delta shear zone, control the location of reef structure and magma placement. Astenospheric melts, reaching in carbon, fluorine, chlorine, sulfur penetrate the overlying subcontinental lithospheric. And this is important because when they penetrate that, they cause extensive metasomata, and that's where the carbonatites come from. So metasomata, subcontinental lithospheric partially melt, producing alkaline and carbonatite magnets. Now, the other thing that one must understand, the carbonatites, and indeed the kimberlite, are part and parcel of the large ischius province. Lips, large igneous, so a large igneous province, and you have associated carbonatite kimberlite. So if you have a carbonatite somewhere, that carbonatite or kimberlite is part of a large igneous province. When you look at the section like that, it's a model depicting the formation of rift-related microns, syenite, carbonatites, A-type granites, granite, all enriched high field strength elements, and rare earths, of course. And that's what they look like. So you have the carbonites shown by C, you have a phonolite, syenite, the phonolite, they all related rift system. This is where it comes from. Quite recently, is a review in economic geology, for your information, published in 2016, volume 8, rare earth and critical elements in all deposits. I was up to review that, pretty good actually. And recently, a book published by Nikolai Vladikin on alkaline rocks and kimberlite, published in the Springer. Unfortunately, 2 weeks after he published that, he passed away. Thank you for your attention.
Thank you so much for that. Really appreciate you coming on.